Fundamental to computer science and cryptography is the study of prime numbers. Now, prime numbers are something that we've studied before in grade school. In fact, my daughter is studying them now as I record this video. They are incredibly important in making the encryption process work, and they're really quite fascinating and beautiful. So in this video, we'll kind of just give an overview of some of the ideas behind prime numbers, which you may already recall. So an integer can be one of two possible types of integers. It could be a prime integer or it could be a composite integer. An integer p greater than 1 is called prime if the only positive factors of p are 1 and p. A positive that is greater than 1 and is not prime is called composite. So we may recall that, for example, 3 is a prime number because its only factors are 3 and 1. 5 is a prime number because its only factors, integer factors, are 5 and 1. So these are prime. But 6 is not prime because although every number has as its factors itself and 1, additionally it has the factors of 3 and 2. Therefore, this number would be considered composite. Now, in general, it's kind of difficult to look at large numbers and be able to tell whether or not they're prime. And therein lies one of the most powerful components of RSA encryption, this idea that very large numbers are difficult to factor. And there exists something called a trapdoor, which we'll talk about when we deal with RSA encryption, and it has to do with primes. And we can kind of go on with this for a long time. The fundamental theorem of arithmetic is one that we've learned. Maybe we don't recall it being called this, but it basically is a theorem that tells us that every integer greater than 1 can be written uniquely as a prime or as the product of two or more primes, where the prime factors are written in order of non-decreasing size. So the key here is that this is unique. For instance, we could pick the composite number 12, and we can start to break this up into prime factors. So we know that the first few prime numbers are 2, 3, 5, 7, 11, 13, and the list goes on. In fact, infinitely, as we'll soon describe. So the first thing I can do to create this factorization is I begin by dividing by 2. So over here I have one factor of 2 and one factor of 6. Now the reason I've written this is because this is already a prime, and that cannot be decomposed further into factors of unique primes. 6, however, can be rewritten as the product of two primes, 2 and 3. Now, in this case, I continue dividing by 2 until I can no longer do it, and then I ask myself, can I then take the remaining factor and divide it by the next prime factor, which in this case is 3, so 3 is already a prime, and therefore I can stop and I can say that 12, in order of non-decreasing size, which means essentially increasing size, so 12 can be written as the product of 2 times 2 times 3. 26, for example, can be written as, well, first of all, I'll try to divide by 2, which I can. So that gives me a prime factor of 2 and 13. Now, 13 I can't divide by 2, so I move to the next prime number. 13 isn't divisible by 3, it's not divisible by 5 or 7 or 11. In fact, 13 itself is prime, so 26 can be expressed uniquely as the product of two primes, 2 and 13. We can pick on another one. We can say 18. Well, 18 is divisible by 2. So 2 leaves a remaining factor of 6. Excuse me, not 6, 9. And 9 is not divisible by 2, so I move to the next prime, which is 3. And it does have a factor of 3. And then it leaves a factor of 3, which is already prime. And therefore I can write 18 as 2 times 3 times 3. So this fundamental theorem of arithmetic is incredibly valuable because it essentially tells us that every number can be uniquely decomposed into a product of prime numbers. Here's another theorem, and this is a useful one because it allows us to potentially hunt for what could possibly be the largest prime divisor of a number. So if n is a composite integer, so it has to be composite, because if it's prime, then it's prime, then n has a prime divisor less than or equal to the square root of n. Okay, well, let's think about this. So that means if I write n as a product of, let's say, two numbers a and b, and I'm just going to point this out sort of intuitively, if a is equal to the square root of n, if a is equal to the square root of n, then the only value left for b would be the square root of n. Now this is allowing the possibility that these aren't, square root of n may not be an integer value, but if one of the factors is the square root of n, and we know that the square root of n times the square root of n is the square root of n squared, and the square root of n squared is n, then if that factor were to exceed square root of n, like let's say square root of n plus 1, if we had a is equal to the square root of n and b is equal to the square root of n plus 1, then our product would be the square root of n times square root of n plus 1, which would give me here square root of n times square root of n is n, and square root of n plus 1 is the square root of n. And we can already see that this is bigger than n. So a little bit of intuition there. If you are looking for the largest prime divisor, for example, if we back up here and we look at 12, then the largest value that, the largest prime that could possibly divide 12, well, the square root of 12 is 3 point something, and therefore if we round that down, 3 point something, square root of 3 lies somewhere right here, that means that the largest prime factor that could possibly divide 12 would be 3. And that could potentially help us generate a list of primes up to the largest possible prime. And you can imagine the computing power that we could gain with this. A computer kind of knows where to stop before it even starts. So a very little useful theorem. So how do we hunt for primes? How do we find primes? Nowadays there are lots of primes, and the largest prime is very, very, very big. I'll let you look it up. And I don't know right off the top of my head, but there are computers running as we speak, hunting for the next largest prime. And finding the next largest prime requires more time than it did to find the previous prime, since the primes tend to be spaced farther and farther apart. So the sieve of Eratosthenes, I can never say his name properly, the sieve of Eratosthenes, you can say that however you like, came from this mathematician, philosopher, of how to identify primes. Well, the idea here is that if you list out the integers that are positive, and also bigger than 1, and you want to find all the primes in that list. So let me just list out up to 10. And the idea here is that, first of all, you can exclude any even number, because other than 2. So excuse me, maybe we should start actually at 3. So if we start at 3, we see that 3 is in fact a prime, and its only factors are 3 and 1. Okay, any even number bigger than 2 is not prime, because 4 has 2 factors of 2, 6 has 3 factors of 2, so you can immediately eliminate even numbers bigger than 2. So 2 does actually belong here, but any multiple of 2 will not be prime. Now identify the next number as a prime number. Well, any multiple of a prime number is not a prime number because it's exactly divisible by that prime. So any multiple of 3, which would be 6, 9, those I can eliminate. And so then I move to the next number not removed from the list, which would be 5. And so I ask myself, is that a prime? And in fact, 5 is a prime. And then I look at any multiples of 5, and I can remove those because those numbers are all divisible by 5. Therefore, 10, which is already crossed out, would be eliminated, 15, etc. And then I move on to the next number not dropped out of the list, which in this case is 7. And then I can remove all multiples of 7 because I identify that as a prime. So we don't have to check every number for primality. We can sort of use this algorithm to first of all eliminate all even numbers bigger than 2, and then find the next number, identify if it's prime. If it is, then we keep it. If it's not, then we remove it. And then we can cross out every single multiple of that prime, since every multiple of a prime is exactly divisible by that prime. And this is an algorithmic way of identifying primes. Now, this will require a lot of computing power as these primes get really, really large, and checking to see if they're prime can require a ton of computing power. We won't go into how we would actually implement this, but we could check divisibility of a number by every number leading up to the square root of n, or the integer that's less than or equal to the square root of n, and work our way up from there. Now, this is by far one of the most interesting ones. There are infinitely many primes. Now, how could there be infinitely many primes, and how do we know that there are infinitely many primes? After all, we don't have the full perspective of all numbers in the world. So identifying infinitely primes can kind of be proven by this idea of contradiction. And this is not a technique that maybe we've looked at yet, but we can basically assume that there are finite primes, or there's a finite number of primes. Okay, well, what that means then, by the fundamental theorem of arithmetic, and what we're going to establish here is that one of these two statements has to be true. There are finite number of primes, or there are infinitely many primes. They can't both be true statements. It's a binary situation. So if we can show that it's not possible for there to be a finite number of primes, then we've eliminated this and we can say there are infinitely many. So we're going to start with kind of the what we call the negation of the statement, and we're going to show that the negation of the statement can't be true. So if there are finite primes, then that says that if there's some integer, some positive integer, that we'll call this integer a. Well, by the fundamental theorem of arithmetic, there exists a prime factorization, which I will just allude to as p1 times p2 times p3. And since there's a finite number of them, I'll just say that there are n primes. Okay, now some of these may be repeats. It can be 2 times 2 times 3 times 3 times 5 times 5 times 5, etc. But that means that there's a finite number of primes. But we know that a isn't the largest number. In fact, we can form a new number that we'll call a plus 1, which will be the product of all of these primes. Plus 1. Right? We've taken the product of all of those primes plus 1. So herein kind of lies the contradiction, because if every number can be factored into a product of primes, and here we're saying that there are n primes in total, then by increasing this number by 1, notice that this new number here is not divisible by p1, p2, or pn. Okay, and I should have pointed out, let's just say that these were all the primes. I kind of mentioned that these could be repeats, but let's suppose p1 through pn are all the primes. So in other words, what I'm doing here is I'm multiplying all these primes together. So none of these primes, p1 through pn, could possibly divide this number, again, because if I take this whole thing divided by, say, p3, then this first term here, I can cancel out a p3, but 1 is likely not divisible by p3. In fact, it's not, because there is no prime number that divides 1. Therefore, what must be the case is there's another prime that's not mentioned in here. So there must be another prime. Therefore, by fundamental theorem of arithmetic, there must be another prime. Let's call it p sub n plus 1. that does divide this. Since none of the existing primes do, and since by the fundamental theorem of arithmetic, every number can be factored into a product of its primes, this forms a contradiction. And sometimes you'll see mathematicians write it as two arrows clashing together. In other words, it cannot be the case that there is a finite number of primes, and you could say, well, what if we added Pn plus 1 in there? Well, then I could do the same thing and say P1 times P2 times all the way up to Pn plus 1, and if we increase that number by 1, now we face the same problem again. There must be some other prime that does divide that new number. And this forms kind of an interesting type of proof called a proof by contradiction. Now, you don't necessarily need to replicate this at this moment. This is just kind of why we can say some of the things that we say when we talk about there being infinitely many of something.